Today we're going to talk about matter, atoms, and molecules, the basis of chemistry. Let's look first at some definitions. Chemistry is the study of matter and all of its changes, all of the reactions and everything that occurs with matter. It's also called the central science. Matter is anything that has mass and occupies or takes up space. Mass is the amount of matter, but weight is actually the gravitational force on the mass. So remember, mass and weight are not the same thing. Energy is your ability to do work or to transfer heat. Laws are general statements based on the observed behavior of matter to which no exceptions are known. They are different than a scientific theory, which is developed by proving or disproving a number of hypotheses. Let's also look at the states of matter. Matter exists in three different states, either the solid state, the liquid state, or the gas state. Remember, a solid has definite shape and volume. Liquids have a definite volume, but they assume the shape of their container. Gases have no shape or volume and completely expand to fill the volume of their container. We change states by either heating or cooling. So a liquid that is heated will come and form a gas as it boils. A gas will condense to form a liquid, and the liquid will freeze upon cooling to form a solid. Matter has different chemical and physical properties. Chemical properties are those that are observed during a chemical change or a chemical reaction. This changes the composition from one compound to another. This happens in rust, in cooking, any other kinds of chemical reactions that we might see. Physical properties are those that are the result of the physical state that the compound lives in. We can change state from solid to liquid. That's a physical property that's being changed. There are other properties such as density, color, or solubility that refer to physical state of matter, not a chemical reaction. There are also extensive and intensive properties of matter. Extensive properties are those that depend on how much substance you actually have, such as its weight, how much it weighs when it's on a scale. Intensive properties are those that do not depend on quantity. Lead will always have the same density, whether you have a little bit of lead or a lot of lead. Substances are identical in composition and properties, but one substance is different than another substance. Elements cannot be decomposed into smaller substances via chemical reaction. An atom of vanadium is always an atom of vanadium, and an atom of lead is always an atom of lead. The elements' symbols will be found on the periodic chart, and we will talk about them in a few minutes. Compounds are what you get when you take two or more elements and combine them in a definite ratio by mass. They can be further decomposed into their constituent elements, such as water being broken down into hydrogen and oxygen, or carbon dioxide being broken down into carbon and oxygen. Hydrogen, oxygen, carbon, those are elements in their base form. They cannot be further broken down like a compound can. A mixture happens when you take two substances and just mix it together. You probably do this at home all the time. Mixtures can be homogeneous, say like, ketchup, something like that, versus a heterogeneous mixture that might be Italian dressing or chocolate chip ice cream, for example. Now we're going to look at how we developed our current understanding of the atom, going way back into the early Greek theories. Early in the 400 BC time frame, it was thought that matter could not be divided indefinitely. This is how we first came to arrive at the theory that there was a limit to how much you could decompose something. In 350 BC, a famous philosopher, Aristotle, said that he felt that Matter was made up of 4 elements, in quotations of course: earth, fire, water, and air. Of course he was wrong, but this theory lasted for over 2,000 years before we discovered a number of actual elements outside of earth, air, fire, and water. John Dalton was the first person to really propose what is our current modern atomic model. And he did this based on a number of experiments, not just on reason like our philosophers would have done. He came up with his atomic theory, and it accounts for the law of conservation of mass, that atoms are neither created nor destroyed, you cannot break them down any further, and the law of constant consumption that says that the elements combine in definite ratios to make the compounds. Dalton's full atomic theory in 1808 is shown here. Again, an element is composed of small indivisible particles called atoms. They cannot be further broken down. All atoms of an element have exactly the same properties. All atoms of another element also have all the same properties of that element. Then, between the two, they differ. Atoms cannot be created, destroyed, or transformed, but they can be combined with other atoms to form compounds. And this happens in whole number constant ratios. A carbon dioxide always has 1 carbon and 2 oxygens. Chemical reactions are what actually does this rearranging and recombining, but it never actually destroys the original atoms. Dalton tried to also add electrons to his model. In a number of experiments using cathode ray tubes, he found that there were negative, what we now call subatomic particles in all atoms. They're called subatomic because they're part of the inside of the atom and therefore smaller or sub to the atom. His model was the billiard ball model initially. He said that atoms are solid and indivisible. Initially, people didn't believe, including Dalton, that there were electrons inside the atom. However, this was proved wrong by Thomson, who developed what he called the plum pudding, I think of it as tapioca model, in the early 1900s. And he found that there were negative electrons in a positive soup of the atom. Rutherford's model, though, came about in around 1910. He discovered that atoms are actually mostly empty space, but that the negative electrons orbit a positive and very small nucleus. He did that through a little experiment that is shown here. Alpha particles, basically positive radioactive particles, were hit into a piece of thin gold foil. And if there was nothing positive inside the gold that it's hitting, then these alpha ray particles would pass straight through to his screen on the other side. And many of them did. Most of them just hit into empty space. However, if they came near some part of the atom that I guess happened to be positive, they would be slightly deflected. Remember, positive and negative charges attract one another, but 2 positive charges would repel one another. This led to the theory that there must be a core nucleus that is positive, and this thing also holds most of the atom's mass, as it could deflect away these alpha particles. So here's what we now know about the nucleus. The nucleus was found to be composed of 2 kinds of particles. One of them is called a proton, and it's positively charged, and its mass is about the same as a hydrogen atom. Since protons have a positive 1 charge and electrons have a -1 charge, every time you have a proton, you'll have an electron as long as it's a neutral atom. There are additional particles inside the nucleus called neutrons. They have no charge, but they do have mass. Then later on came Bohr. Bohr showed that electrons actually orbit the nucleus in what we'll refer to as shells. Think of a dartboard with a central bullseye and a number of rings around the outside in which the electrons could live in different shells. Then they can move from one shell to another shell if you've put some energy into them. This slide here is a review of the modern structure of the atom. It's a review of the slides that we've just talked about. Again, an atom is mostly empty space, but has a small, very dense nucleus in the center. And that's where most of the mass is for that atom. Atoms are composed of three pieces: protons, neutrons, and electrons. The nucleus has the protons and the neutrons, but not the electrons. Electrons are small, and they move around the outside of the nucleus. Here again are the three particles, electron, proton, and neutron, with their symbols and their masses in something called AMU, which is atomic mass unit, how big they are, and their charge. Now, having looked at all the particles and the overall structure of the atom, now we're going to start examining the periodic table. The periodic table is the way that scientists have organized the elements that we know. The elements are grouped in either groups or families. Those are the columns on the periodic chart. And then they are grouped in rows called periods. Each period shows the pattern of properties repeated in the next period. I'm going to switch to show you a periodic table in the next slide. Here is a periodic table right here. And this picture, it's only showing you part of it. Beginning with number 1, group and period, we have group 1 going across 1, 2, 3, 4, 5, 6, 7, all the way through 18. And then we have the periods 1 through 7 all the way down, right there and right there. Now you'll see that there is a blue section, a yellow section, a pink section, and a green section. The blue section is for the alkali and alkaline earth elements. The yellow section is our noble gases, some of our metals, and most of our nonmetals. The center is our transition metals, and the bottom is our lanthanides and actinides. Now, I picked this periodic table as one that is on a slide coming up because it's interactive. And so I could click here on one of these elements, such as titanium, and it will bring up for me data on titanium. In just a second, there it goes. And I can read all about titanium. So there's the symbol for the element, okay? There is a statement about titanium and what it is and what it does. All of the properties of titanium, what group it's in, what period it's in, what it looks like, what its atomic number is. And up at the top here, it has the compounds that it makes, and periodicity and other things that you can click on. So this is an interactive periodic table, which is one of the reasons why I picked it for you to look at. Okay, I'm going to close this screen and go back to my other screen and bring you back to where we were. Okay, so now I've talked to you about these. Their main group, those are the representative columns. Those are the blue and the yellow in that periodic table that I just showed you. The transition metals were in the center, and the bottom rows were the green ones that were the metals, the inner transition and the rare earth, lanthanides and actinides. The periodic table that I just showed you was found at www.webelements.com. If you click on this now and keep it open, or copy it into your browser and keep it open, you'll be able to follow along in the next sections. There's also one in here that has these cool QR codes. If you want to use your mobile phone, you can click on the QR codes for each one, and it will bring up the information about the element on your phone. And just for fun, this is a YouTube video that is really kind of cute about all the different elements, and I thought you might find that interesting. Okay, now here's the periodic table as it's all shown in one slide. Again, group 1 through 18 going across, group 1 and rows, and then, period 1 through 7 on the way down. Okay, the number at the top here is the atomic number 1, 2, 3, 4, all the way now through what we know up through 118. These pink colored ones and purple colored ones really kind of belong right in here, but we pull them out at the bottom so that the periodic table is not too long for you to see. All of our nonmetals are on this side. These are the noble gases in 18, the halogens in 17. A number of this kind of stair-step thing right here separates our nonmetals and our metals, and you'll see that on another slide. The transition metals are in the middle. Okay. So there's over 112 known. There's actually 118 now. 88 are found in nature. The rest have been man-made. And remember, elements cannot be decomposed into any other substance from a chemical reaction. There's some other things that we should talk about. Abundance is how much we find in the earth, typically, or in the human body. That'll be reported. Each element has a symbol. That symbol is either one letter, one large capital letter, or if it's two letters, it has a capital letter first, and the second one is lowercase. So if I go back to that periodic table, I can show you that vanadium is just V, boron is just B, but copper is Cu, from an old terminology that we no longer use, but that's how the symbol got there. Molybdenum is Mo. Beryllium is Be. Two letters, the second one is lowercase. Okay. Here are the abundances of some of the elements in the Earth's crust and atmosphere. Oxygen is highly abundant, as is silicon, aluminum, iron, and many others. In the human body, however, we have a lot of oxygen as well, carbon, hydrogen, nitrogen, a little bit of zinc, and many of these trace elements are found in the body. Okay. The number, the atomic number, is the number that represents how many protons are in the nucleus. We give it the symbol Z, and all of the elements on the periodic table are numbered consecutively by this atomic number. The atomic number determines the element. The number of protons in the nucleus determines which element you have. The number of electrons in a neutral element is equal to the atomic number. If, for chance, the atom is charged, meaning it carries a positive charge or a negative charge, that means it has a different number of electrons than it does protons. If it's negative, it has more electrons than protons, and if it's positive, it has more protons than electrons. So if I go back to my periodic table, I know that lithium, Li, must have 3 protons. It also, if it's neutral, has 3 electrons. I know that bismuth, number 83, has 83 protons, and therefore 83 electrons, unless it is charged. In addition to the atomic number, there is also a mass number. The mass number is A, and it is the sum of the number of protons and neutrons in the atom. So Z is the number of protons, N is the number of neutrons, and so atomic mass, A, is the number of protons, and it's because it's mass, and the number of neutrons. We use this and write these very common symbols right here, A at the top for the mass, Z at the bottom for the number of protons, and E for the element symbol. So carbon-12 has a mass of 12, and it has 6 protons. Calcium has a mass of 48, and it has 20 protons. Gold, a mass of 197 and 79 protons. If you pull up the periodic table from either one of the links that I gave you or from any other link that you find on the internet, you can now look up these other atoms at the bottom, nitrogen and copper. Let's look for them. When I come over here and I look for nitrogen, I find that it is atomic number 7 and its mass is 14. Okay. So its mass is 14, as we said right there, but its atomic number in that question mark there should be the number 7. Copper, let's look at that one next. Copper, Cu, is down here, right there. Copper has the atomic number 29 and a mass of 63. And so its mass is 63, its atomic number is 29. Now, what if we find out which element it is that has a mass of 18 and atomic number 8? Well, if I scroll up here on my periodic chart to see that the mass, the atomic number 8 and the mass is 16, that seems a little odd. It's going to be the atomic number 8 that dictates which element it is. So it's 8, and it's oxygen. But what did I write over here? I said 18 was the mass, not 16. That is an isotope of oxygen. That means that it has 2 extra neutrons in the oxygen, and it's not just a weight of 16. So be careful that you always look for the atomic number down here, or down here to determine which elemental symbol you would write. Isotope. So here it is right here. Isotopes are atoms of the same element, but they have different numbers of neutrons. Isotopes have a different mass A value, but are the same element. Here's an example of other isotopes besides that oxygen example on the prior slide. Hydrogen typically is found in the number 1 isotope called protium. 1 proton, no neutrons, 1 electron. Deuterium, though, is the second most abundant form of hydrogen. It has 1 proton because it's still hydrogen, but it also has a neutron. And tritium is the radioactive form of hydrogen. It has 1 proton, but it has 2 neutrons, giving it a mass of 3. Here are some more that you can do. Here is oxygen in its normal form, 16 and 8, and 18 and 8, the one we just did. Uranium also has a number of isotopes, uranium-238 or uranium-236. Note the 92 is still there. That dictates that it's uranium. Okay. We now have, and then over here we have some ions, so let's not look at those until we do these first. Now, oxygens have 8 protons, and they have 92 protons in uranium. The way that you find out how many neutrons there are to subtract 16 minus 8. Well, that would leave us with 8 neutrons. 18 minus 8, that would give us 10 neutrons in oxygen. Uranium you can do, you can take 238 minus 92 to get 146, I believe. Yep. Or 144 neutrons, doing the subtraction. Okay. Now these ones over here are all charges. They all have charges, okay? So we know it's sodium because it's atomic number 11. It has 11 protons. Wonder how many electrons it has. If it had 11 electrons, it would be neutral. But it's 1 more positive, so it only has 10 electrons. Calcium is 2 positive, and so instead of having 20 electrons, it only has 18. Bromine is a negative charge, so instead of having 35 electrons, it has 36. And in sulfur, instead of having 16 electrons, it has 18 electrons. The number of protons are always the same, 11 for sodium, 20 for calcium, 35 for bromine, and 16 for sulfur. And then we subtract 23 minus 11 to get the number of neutrons. There will be 12 neutrons in sodium. There will be 20 neutrons in calcium, and you can do the other two. Here are 3 examples for you to work out. I will give you a few minutes. Okay, so Atomic number 12, if I look at my periodic chart, atomic number 12 represents magnesium right here. Magnesium, number 12. That's Mg, number 12. 79, element number 79, I look over here, is gold. And element number 7 is, right here, nitrogen. Now, they're all neutral, so there are 12 electrons in number 1, 79 in number 2, and 7 in number 3. And then you subtract 24 minus 12, you get 12 neutrons, 200 minus 79, or 15 minus 7. These should be pretty simple problems for you to do if you were asked to do them on any kind of exam. Okay. The weight that you see at the bottom of the periodic table underneath each element is the weighted average of all of the masses of isotopes for that element. So while we may not carry these digits out to 3 or 4 decimal places, you should just know that those masses are a weighted average. Okay. Now let's look at the periodic table in a little more detail. The periodic table is arranged into metals, nonmetals, and metalloids. Remember, there are groups or families. Groups are the vertical groups of elements on the periodic table, running 1 through 18. They have similar chemical and physical properties if they are in the same group. The periods run horizontally 1 through 7. They represent the transitions from the metals on the left to the nonmetals on the right. And then there are 3 regions: metals, nonmetals, and metalloids. So if I pop back to my periodic table, okay, there are metals here. Aluminum right in here. These are our metals. Aluminum, and then see, that comes right in here under boron, and then right here, and then right here, and then right here, here. It's not really dark enough right in here to see it. There should be a little darkened region right in here. The ones right along the edge of this, going kind of diagonal, are our metalloids. And then these are our nonmetals. That's kind of the transition place between all of our metals and our nonmetals. Okay. So if we look at some of the periods going across, okay, if we look at the second period, it goes from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon going across on the periodic table. Lithium is the metal, neon is a non-metal. If we look at a vertical group or family, one of them in the transition metal row is chromium, molybdenum, and tungsten. And I'll show you those. Chromium, molybdenum, and tungsten are shown here. Chromium, molybdenum, and tungsten, and seaborgium now, and that is in group 6 on a periodic chart. Okay, so here's the periodic chart again, and this shows you the metals, nonmetals, and metalloids. And here's that stair step I was telling you about that's listed in green. Those are our metalloids, and then our nonmetals to the other side, and our metals to this side. Hydrogen is kind of in the wrong place, but we won't talk about that right now. Just know that hydrogen is a nonmetal, even though it's written on the left-hand side of the periodic table. Most of the elements are metallic in character. Only 20% are nonmetals, and the metalloids are kind of right in between. Metals have different chemical properties than nonmetals. Metals have very few electrons in the outside shells, where we talked about where the electrons can live. They form cations. They form positive charges by losing their electrons. They then have less electrons than they do protons. They form something called ionic compounds with the nonmetals, and we'll talk about compound formation in the next section. They make metallic bonds, and they conduct heat or electricity. They can be pounded and hammered on. Think of iron. You can make things out of it. And most of them are solids, except for one, mercury. It is liquid. Okay. So here are our metals. Groups 1 and 2, our group 1 is our alkali metals. Groups 2 is our alkaline earth metals. Okay? And they're shown down here: beryllium, magnesium, calcium, strontium, barium, and radium. Groups 3 to 12 are our transition metals, and then we have our lanthanides and our actinides in our metals. Nonmetals have the outer shells containing more electrons. They make anions, or negatively charged compounds, by gaining electrons. They tend to have more electrons than they do protons. They form ionic compounds with metals and covalent compounds with other nonmetals. They form covalently bonded molecules, which means that they share their electrons. We'll talk about that later. And the noble gases are monatomic. They can be insulators, and they have full shells. They are poor conductors, and they typically are gases or solids, except bromine is a liquid. Group 17 nonmetals consist of what we call the halogens: fluorine, chlorine, bromine, and iodine, each shown here. Group 16 nonmetals are chalcogens: oxygen, sulfur, selenium, and tellurium. Our noble gases, or our inert gases, are non-reactive gases for the most part: helium, neon, argon, krypton, xenon, and radon. Other groups listed in group 13, headed by boron, group 14 by carbon, and group 15 by nitrogen. We will now look at the formation of molecules. Molecules are the smallest particle of an element that has a stable, independent existence. You have to have two or more elements bonded together to get a molecule. There are some examples of molecules shown below. Dihydrogen and dioxygen, that's two elements of hydrogen, or two atoms of hydrogen bonded together. Two atoms of oxygen bonded together to make O2. Sulfur 8, water, methane, CH4, and ethanol, C2H5OH. These are molecules. Notice that they are made, in this case, to be a molecule, they're made of almost all nonmetals. Okay. We use these formulas, as written like on the other page, to describe our compounds. Compounds are distinct substances that are composed of two or more elements. You describe the compound by describing the number and type of each atom in the simplest unit of the compound. Each element is represented by its symbol. The number of atoms of each element is written to the right of the element as a subscript. If there's only one atom, the one subscript is not written. There are also something called polyatomic groups, and they are placed in parentheses if there's more than one. You have a sheet in the materials of your common ions. So we write chemical formulas to show how all atoms and molecules combine. They show the total chemical structure of the substance. Helium, gold, and sodium, that would be a monatomic element. You can actually have helium, gold, or sodium around. Some elements exist as diatomic, meaning two di molecules. Oxygen, hydrogen, chlorine, fluorine, iodine, nitrogen, and bromine exist as diatomics. Everything else on here are compounds. Water, salt, and sucrose, sugar, are shown there. Water is H2O, table salt, sodium chloride, and sugar. They have two or more elements bound together. So when I look at how these formulas tell me something about a particular molecule, I can see that here. If I have the formula HCl, I have one atom of hydrogen and one atom of chlorine. H2O, two atoms of hydrogen, one atom of oxygen. Ammonia, NH3, one atom of nitrogen, three atoms of hydrogen. And then in C3H8, which is propane, I have 3 atoms of carbon and 8 atoms of hydrogen. The chemical compounds are made through the formation of chemical bonds. Bonds can be either ionic or covalent. Ionic bonds are made when two things that have charge, either one positive and one negative, come together. One having the negative charge gives this electron to the one having the positive charge so that they can get back to their regular neutral state. Covalent bonds, though, result from nonmetals sharing electrons. Again, in the formation of an ionic compound, an ion has to exist first. An ion is an atom or a group of atoms possessing a net electrical charge. They can either be positive cations, they have lost an electron, they have more protons than they do electrons. Or they can be negative ions or anions, meaning they have more electrons than protons. Usually this will happen when I take a metal and combine it with a nonmetal. So if I have metals, such as sodium with a +1 charge, calcium with a +2, or aluminum with a +3. Ammonia is kind of a different one. It's a polyatomic cation that you just have to remember. It's called ammonium ion. Negative anions, they lose their electrons, so I get fluorine negative or fluoride, oxygen with a -2, and nitrogen with a -3, that's nitride. I also have polyatomic anions, sulfate, SO4 with a 2-, phosphate, PO4 with a 3-, and carbonate, hydrogen carbonate, HCO3-. Again, there's a sheet of ions in the materials that you were given for you to refer to when writing these compounds. Ionic bonds are formed by the attraction of the cation and the anion for each other. The metal reacts with the nonmetal to form the compound, such as sodium chloride. So here are some reactions. I can react group 1 metals that make a +1 cation with group 17 nonmetals which make a -1 anion. So lithium and fluorine make lithium fluoride. Potassium and bromine make potassium bromide. You'll note that these equations are completely balanced. I have 2 lithium atoms on the left and 2 fluorine atoms on the left of the arrow, and I have 2 molecules of lithium fluoride on the right, 2 lithiums and 2 fluorine. Same thing with potassium. I have 2 potassium atoms here. I have 2 bromine atoms here because I have this 2 down here. And I get 2 molecules of potassium bromide on this side. This has to happen this way because these 2 are diatomic, so there has to be 2 there at all times. And so I have to combine 2 lithiums or 2 potassiums with them. Here is a full chart for what happens with everything on the periodic table that makes ionic compounds. If I react groups 1 and 17, I get them in the formula MX. 2 and 17, I get MX2. 13 and 17, MX3, and so on. So the examples are shown to the right. If I combine a group 2 metal with a group 16 nonmetal, I've got something with a +2 charge and a -2 charge, and so I get BaO, or barium oxide. And then group 13 and 16 is the most complicated form, M2X3, so aluminum sulfide. A couple more. Groups 1 with 15, 2 with 15, and 13 with 15. Hydrogen can also react with some of the metals, since it is a nonmetal, to make a hydride. Lithium hydride, potassium hydride, calcium hydride, and barium hydride. Everything else that's ever made with hydrogen is covalent. You've heard me say the names of these compounds as I have been talking, and now here's how you will also learn to make and name these compounds. Remember, binary compounds, bi meaning 2, are always made of 2 elements. In this case, a metal and a nonmetal make an ionic compound. If we were to react 2 nonmetals together, those will make covalent compounds. We will always name the metallic element first, using the element's full name. And then we will take the less metallic element and change its ending to IDE and give it that name. So here's some examples. If the element were boron, the stem is bor. Carbon, carb. Nitrogen, nitre. fluorine, fluor, chlorine, chlor. So we just kind of truncate off some of the end of that element's name. Here are some more. Phosphorus, selenium, sulfur. There shows their truncated names. Now, we want to name them. Remember, ionic compounds are a metal and a nonmetal. The metal is positively charged, and the nonmetal is negatively charged. Cations are named first, and anions are named second with the IDE ending. So lithium, being the metal, gets its full name. Bromine is not bromine, but bromide. Magnesium chloride, lithium sulfide. So I wonder what you think the next one is. I'll give you a second to answer. Did you get aluminum oxide? I hope you did. What about this one? Na3PO4. What's first? And what do you do with the P? Did you say sodium phosphide? I sure hope you did. What about this one? Magnesium nitride. Here are all of the answers to those compounds. Now we want to name other ionic compounds. Sometimes some of the metals can have more than one charge. I haven't really talked about that very much. And you will note from your handout that they are all listed there if they make more than one charge. Okay? Most of the transition metals are the ones that make more than one charge, as well as the metals in group 13, except aluminum, which is always just a +3. And then groups 14 and groups 15 metals also typically make multiply charged cations. When you're talking about naming the multiply charged elements, there are two methods. The older method changed it around a lot and used the IC or the OUS to indicate the oxidation state. We won't really do that method that often. It's not the modern method, and it's a much more difficult method. The easier method is to just use the Roman numerals to give out the metal's oxidation state. And so, for example, right here, there are two ways that you can have iron bromide. Iron, where the +2 iron or a +3 iron that reacts with bromine. So in the old system, those would be ferrous or ferric bromide. But really, it's easier just to say iron 2 bromide or iron 3 bromide. Tin is SN. Stannous oxide or stannic oxide for tin with a +1 or a +2. But it's really, I'm sorry, with a +2 or a +4 on the tin. It's really easier to say tin 2 or tin 4 oxide. Cobalt is either a +2 charge or a +3 charge. So if it's cobalt 2 chloride for the +2 charge, it's what for the +3 charge? Right, it is cobalt 3. The lead one will be lead with a +2 charge or a +4 charge. So if it's lead 2, right. And if it's lead 4, right. Lead 2 sulfide or lead 4 sulfide. Note the older names are shown here, cobaltic and cobaltus, and plumbus and plumbic, but I do not expect you to know that. There are also polyatomic ions that you will have on your sheet that you could memorize their names. Hydroxide, cyanide, and ammonium, for example. And those make binary ionic compounds as well. KOH, with all of them capitalized, is potassium hydroxide. You have to recognize that the OH is an ion with its own special name together. Barium hydroxide, hydroxide had a -1, barium has a +2. This gives us barium hydroxide. Aluminum hydroxide has 3 OHs, that would be aluminum hydroxide. Now to make it complicated and put everything together, what is the name of the compound shown below? FeOH2. You're right, it's iron 2 hydroxide. What about the next one then? Exactly, it's iron 3 hydroxide. You have to keep this formula together, this polyatomic OH or the cyanide or any of the others on the sheet together. How about BaCN2? Can you do that one? It's barium cyanide. How about NH4S? This is a tricky one. It's ammonium sulfide. Ammonium is the polyatomic ion. Now I've put two polyatomics together. What are those? Yep, it's ammonium cyanide. Okay. So we've done the names. Now we need to look at how we got those formulas from those names again, just to make sure that it's all clear. Sodium has a +1 charge and chlorine has a -1 charge, and so it's very easy to see that one sodium and one chlorine, one positive and one negative, go together so that the charges are equal. Sodium chloride. Same thing with potassium anhydroxide, which is OH -1 and potassium +1. You should also be able to see that for calcium with a +2 and sulfate with a -2. And you should also have to see that if aluminum is +3, which it always is, and OH is a -1, I'd have to have 3 OHs to get 3 minus charges to make the plus charge of 3 and the minus charge of 3 equal to 0. A simple way to do this is to write them down with their charge, memorize what their charges should be, write the ions down with their charges, and then cross them over and make them into subscripts. That +1 becomes the subscript here, that -1 becomes the subscript here. We don't write the plus or minus, and we typically don't write it when there is a 1. We get lithium chloride. This is helpful for multiple charge things, so calcium with a +2 and fluorine with a -1, if I just bring that +2 over here, it tells me how to write the formula, CaF2. Same thing with aluminum bromide. Bring that 3 over, bring that 1 over, AlBr3. If I go down to barium nitride, same thing, bring the 2 and bring the 3, Ba3N2. The one here for magnesium oxide, if I bring that 2 over and I bring that 2 over, I would never write this Mg2O2. I would just simplify that down to make it MgO, so that these can always be in the lowest multiple available. How about you take a minute and try to write the next 3 formulas? Okay, did you get KCl, potassium chloride? You should. Did you get CuI2, copper 2 iodide? And what about the last one? Bring the 3 over and bring the 2 over. Fe2O3, ferric oxide or iron 3 oxide. Here's another sheet that you could use to do some practice. I won't answer these right here and now. I would like you to practice them. And if you have any problems, please post a question to me, either privately or on the discussion. Okay? Also try these. Write their formulas. You can pause the video at any time to watch these screens for longer to do the assignments. A few more things to talk about as far as naming. We can name binary acids. These always have hydrogen and a non-metal. They are compounds that are gases at room temperature. And they are always hydrogen, the stem, and the IDE ending. So for example, HF is hydrogen fluoride. HCl is hydrogen chloride. HBr, hydrogen bromide. What about H2S? Yes, that is hydrogen sulfide. That is the end of our inorganic naming for the metal and non-metal compounds. Let's now look at our covalent bonding and covalent naming. This is a little bit easier. Covalent bonds are formed when two nonmetals combine. The atoms share electrons. If the atoms share 2 electrons, they make a single bond. If they share 4 electrons, they make a double bond. And if they share 6 electrons, they make a triple bond. Here is a representation of how that 2 hydrogen molecules come together to make an H2 molecule. They approach each other and they're charged. They kind of pull a little bit to the side here, and then they become together. Now there's a little more technical term to that, but for now, just imagine that these things come together and completely share their electrons. When I name these, I should remember too that some of them are diatomic. This is our list of diatomics, as we've talked about already. You should remember which elements are diatomic. Covalent molecular compounds that have 2 nonmetals in them, you have to include a prefix that tells you how many atoms of each element there are. You want to use the minimum number of prefixes, and you usually do not use mono for one of your prefixes. But if the number of atoms is 1, it's mono, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. And so here's how we do it. CO is carbon monoxide. CO2 is carbon dioxide, to show you that there are 2 there. And that allows you to know the difference between carbon monoxide with 1 and carbon dioxide with 2. We then have sulfur trioxide and oxygen difluoride to show you that there are 2. Now, what about this next one? P4O6. Think about it. Yep, tetraphosphorus hexoxide. 4 phosphorus, so you get tetra, and hexoxide because there are 6 oxygens. What about the next one? That's right, tetraphosphorus decoxide. How about these? Dinitrogen monoxide, nitrogen monoxide. See the difference? This one has 2 on the nitrogen and 1 on the oxygen, but this one has 1 nitrogen and 1 oxygen. There's also dinitrogen trioxide and nitrogen dioxide. So you always know how many there are. How about on the bottom 2? Dinitrogen tetroxide. It has how many nitrogens? 2. How many oxygens? 4. N2O4. Dinitrogen pentoxide. What about it? That's right. 2 nitrogens and 5 oxygens. N2O5. There are plenty of opportunities for you to practice your naming and your writing of chemical formulas. Please review all of the definitions and all of the assignments and go through all of the work so that you can be good at this and do very well on any exam that we might have. Here is a review slide of naming if you would like to follow a visual chart. If you have any questions, please feel free to come and see me. I hope you enjoyed this presentation. I'm sorry it was a little bit long, but there was lots of information covered. If you need to review it again, please feel free to do so.